Hi everyone, in this presentation I'm going to explain our study on vision-based obstacle avoidance in drone navigation using deep reinforcement learning. This research was done in collaboration with Dr. Harati and Dr. Ghiasi-Shirazi at Ferdowsi University of Mashhad. First, let's have a look on the outlines of this research. I begin with some introduction and background on the problem, then we proceed to related work. Then I propose our methodology. After that, we have some implementation details, and at the end, I report our experiments and results we obtained from this research. To begin with, it's critical to know that reinforcement learning and robotic tasks have always been in a tight relationship, since robotic platforms are a suitable platform to study rational decision making and incorporate intelligent agents. But after introduction of UAVs as a high degree of freedom platforms, it became much harder to use reinforcement learning, since the localization problem of UAVs is actually hindering the process of using reinforcement learning. And both the continuous state space and continuous action space is the other problem that we encounter nowadays. Our motivation to define such a study was biological entities like fly that would use a combination of sensors like compound eye and gyroscope-like sensors called halter in order to maintain its flight equilibrium and navigate through an environment. So basically, in this study, we try to provide a solution for end-to-end control of our flight system and simultaneous use of imagery input and sensory input in order to do so. Challenges of our study was to design a structure in order to be efficient for the learning process, and design an informative structure, actually like reward function, to be enough for the learning process and agent to make a rational decision. So to overview the related works, we categorize attempts in using deep reinforcement learning for unmanned aerial vehicles into three categories. The first category you can see on the right side is the control problem, which is actually producing low-level commands in order to make the drone stable in the flight. The second task is the navigation part, which is actually avoiding obstacles during the flight. And the path planning would be to follow a target from point A and point B. You simultaneously have point A and point B, and you are in charge of designing or planning a path from point A to point B. We somehow emphasize on navigation and control tasks because we are intending to provide a solution to obstacle avoidance and low-level controller, and we categorize ourselves here in continuous action space and altitude and lateral control of the drone. So as I just mentioned, we desire to use image input and sensory inputs to do so. So we designed our structure like an end-to-end structure like this. The first module is a waypoint generator that is in charge of producing a set of waypoints online, and the second module is in charge of following that waypoint and producing low-level command to do so. So basically, the first module is a deep residual network that would take single image and produce an abstraction of features. Then those features would be fused with sensory inputs and inputted to the second module. The second module is actually actor critique style proximal policy optimization, and our actions would be thrust forces on each rotor. So here is essential to go over our modules. The first module was adopted from one of our references, and we pre-trained it on an original data set provided on that paper also. The first module actually was a deep residual network with 3 residual blocks and a fully connected layer at the end of it. We incorporated such an architecture in our study to have a reliable feature abstraction from the input image. The second module, as I just said, was actor critique style network. The actor was in charge of estimating the parameters of a normal distribution with mean and variance, and then we sample our 4 values for each rotor thrust from this normal distribution. The state space included rotation matrix, linear velocity, position, and angular velocity. This is the product of using feature abstracted from the input image and the sensory input. So the value function, or the critic part of our network, was also in charge of predicting the utility of each state in order to be used in our action estimation part. So the output would be a single V of S that we use in the next part in the details. So the loss function that we used was the traditional loss function in proximal policy optimization paper, which was suitable for variance reduction and was robust against noise and outliers. And the main function of it was to increase the probability of most valuable actions. So our agents gather an episode, and during that episode our critic provide us such estimation of the value. By the estimation, we compute advantage of each state action pair over other possible actions, and we try to not maximize this variable, and as our policy is changing simultaneously, we have to weight it by some important sampling weight by the ratio of change of our policy. So in order to estimate our advantage, it's hard to calculate the Q function and value function and do the subtraction. We use the generalized advantage estimation method in order to estimate our advantage function. We first use our estimate of the value function in the current and the next state in order to measure some delta, and this delta would be used to calculate the advantage. The bottleneck of our study was to design a reward function that would be informative enough for the agent to do the learning process and learn the desired tasks. Such a reward function we designed was based on punishments and would incorporate positional error, rotational error, and errors in the velocity, both in the linear part and angular part of it. Of course, we added some term based on occurrence of crashes and collisions to decrease the probability of having collisions in our training process. This error terms was actually summed by some weights in order to form a reward function. So to overview our implementation details, our inputs were a single RGB image that was provided every 1 second. After receiving such an image, we decided to proceed with 100 steps of simulation. So the sensory data that is going to be fused with the abstracted features from the single RGB image was reading by 100 Hertz, and the simulation steps on the second module would be done for 100 steps. The outputs of our model were a normalized rotor thrust, a vector of 4 values actually, between 0 and 1. 0 would show that the rotors are turned off, and the 1 would represent a full thrust. Then we, after sampling those 4 values, we hard-coded it like an ESC unit based on dynamics of the drone in order to transform them into some angular velocity for each propeller. For the experiments and results, we decided to use robotics operating system and Ghiasi because we hadn't the chance of having actual robots. So this robotic operating system and Ghiasi provided us multiple models of drones and multiple models of environments, but we intended to use the urban environment, so we used this environment you can see here. The experimental platform was also a drone named by Crazy Fly version 2. The actual drone is like the right picture in this slide, which has 27 grams of weight. And on the left side, you can see the simulated version of the Crazy Fly that we use in our study. So in order to evaluate our study, we designed multiple experiments, but first let's overview the learning curves in our study. You can see that in each 10 trials of different random seeds, our agent is successful at learning the desired tasks. On the left side, the collision punishment is being converged to 0. It means that our agent, by the time the learning process is done, is avoiding obstacles and does not experience any collisions. On the right side, the reward function, actually the average discounted reward function, which we call return, is shown during the training process with 10 different random seeds, and it's actually also preventing that our agent is successful in learning such tasks. In the first experiments, we decided to throw our drone with an initial velocity toward the wall and measure its ability to avoid the collision. So from 1 to 10 meters initialization, we have this diagram that would show that in less than 11 seconds, our agent is able to stop from in a safe distance from a wall. On the second experiment, we tried to measure our obstacle avoidance ability of our agent by running our policy in an urban environment. You can see the paths that our agent took in highlighted green paths. So the red dot is actually our drone, and you can see that it can steer away the obstacles in the environment. Here is also the second trial of this experiment, and in order to measure the ability against smaller obstacles, we initialized our drone against some waste basket and ran our policy. Also, you can see the highlighted green paths of our agent in the environment. So at the end, we decided to run our agent autonomously in an urban environment in order to navigate through obstacles and through streets. So we compared it with the human pilot. The splash time for the human pilot was much higher than our policy, so our policy is actually time efficient, but the traverse distance of human pilot is much less than our agent, because human pilot is able to predict the obstacles from much greater distances, but our agent postpones its decisions when it comes to an obstacle, and it's much more flexible than human pilot. You can see it on the collision report that our agent experienced 5 collisions, but the human pilot experienced 3 collisions. It's basically because that our agent is lack the ability of seeing traffic light or recognize the traffic lights in the street, but the human pilot is crippled in tight areas and it's not enough flexible, but our agent is flexible enough to do the navigation task in tight areas. So we think that our study was a good start in order to use deep reinforcement learning and simultaneous usage of image and sensor inputs in order to do the navigation tasks of drone or quadrators with the ability of avoiding obstacles. We concluded that with the use of some state-of-the-art neural networks such as LSTMs or GRUs, it would become much easier to do the same tasks, and we try to study it for our future studies. Thank you for your attention, and I'm here for your questions. Thank you.